Now, in the last lecture, we looked at the general aspects of Ginzburg-Landau theory and how it describes a transition. And here, we will now try and apply this Ginzburg-Landau theory for superconductors. So, we will have to write down the order parameter associated with a superconductor and what is the free energy of the superconductor, which is going to be expressed in terms of this order parameter. So now what is the order parameter? So Ginzburg-Landau order parameter for a superconductor. Okay, this is the question that we would like to pose, that what is the Ginzburg-Landau order parameter for the superconductor. Of course, above it there is no order parameter, psi is equal to 0. Okay, but below the superconducting state there is a finite, below the superconducting transition. Now here Tc represents the superconducting transition. For T less than Tc, a finite order parameter develops in the superconducting state, and this order parameter psi is written as psi naught e raised to I phi. It has an amplitude and it has a phase. The order parameter has both an amplitude and a phase. Okay, what does this amplitude represent? The order parameter amplitude represents mod of psi naught square, represents the density of Cooper pairs which are present inside the system. Density of Cooper pairs in the superconductor. It is just directly, psi square is taken directly as a measure of the density of Cooper pairs, because at T greater than Tc, Ns is equal to 0. At T less than Tc, Ns is not equal to 0. Definitely a finite density of Cooper pairs develops inside the system, and so this is an important signature of the order parameter, that you have a finite density of Cooper pairs which are generated. This is a macroscopic quantum state. The psi represents the macroscopic quantum state. Macroscopic quantum state where entire system you describe the entire system with one single phase phi. Okay, so typically the system has entered into a very different phase, because in the normal state you have electrons which are present, but each electron is not in phase with the other electron. Every electron is behaving independently. But once you enter into the superconducting state, you develop a density of Cooper pairs, but also each particle inside the system are all described by one single parameter phase phi. Okay, and this is a very important factor which comes into while describing the superconducting state, namely the phase describing the superconductor. Remember that it is this phase phi, the superconducting phase, which gives rise to the Josephson junction effect. It is this quantity which is giving rise to the Josephson junction effect, the phase phi. One superconductor is in one phase and the other superconductor in another phase. You bring them two together, you can change the phase difference between them by applying a voltage, and the current behaves in a particular way. So all of this game which happens in Josephson junction is because of this phase phi. So this is a very characteristic property of superconductor, namely the presence of this phase. Okay, and the behavior that this superconducting phase, the unique property of this superconducting phase order parameter is included in this quantity psi is equal to psi naught e raised to I phi, where now phi is the phase. Okay, remember that we sometimes use phi to represent flux and sometimes to represent phase. In this case, in this particular case, phi represents the phase. Okay, here we are representing the phase of the superconducting state, okay, that all the particles are in phase with each other, okay. Now the free energy of the superconductor, of course, need not is expanded. The free energy of the superconductor is the free energy density of the superconductor is written in terms of alpha psi plus beta psi square, okay. So beta alpha psi square plus beta psi raised to 4, but there is an additional term, okay. What is this additional term which is present inside the superconductor? This additional term is the kinetic energy of the particles in the superconductor, okay. And this kinetic energy of particles inside the superconductor is basically p square by 2 m star, okay. M star is twice of m, okay, because you have Cooper pairs. So for the Ginzburg-Landau working out, we will now assume that there are pairs inside the system, okay, and so all the working out will be based on that, okay. Now what are the so these are the particles which are present inside the superconducting state, okay, and the kinetic energy of these particles, okay, can be written as p square by 2m, or which is minus I h cross del psi the whole square by 2m star, okay. So this is just the kinetic energy of the particles. This is just the kinetic energy of the particles inside the system. Now what about a superconductor placed? So this would be the additional term which will go in here, okay. So the free energy will have not only these terms, but will have the additional term which is related to the gradient of psi, the kinetic energy of the particles which are present inside the system. What is their kinetic energy? They will also contribute to the free energy which is present inside the system, okay. They will also contribute to the free energy, okay. But what about superconductor? Okay, so this is one contribution that you can consider, but what about a superconductor placed in a magnetic field? Okay, for a superconductor which is present in a magnetic field, the momentum of an electron goes to p minus ea, okay. We know that the canonical momentum, this is the canonical momentum of an electron in a magnetic field. You can write it like this: p, the momentum of the electron p goes to p minus ea, okay. So this would actually be, okay, so so your momentum p goes to, so your minus I h cross gradient of psi minus 2e, okay. If this is a charge q, okay, if it's a charge q for Cooper pair, it is 2e. For Cooper pair, the charge becomes 2e a psi, okay. So your free energy now in a magnetic field, the general free energy of a superconductor in a magnetic field is, first let me write down the terms, plus alpha psi square plus beta by 2 mod psi raised to 4 plus h cross square by 2m star So what we have done is, this is the kinetic energy term. This is the kinetic energy term of a particle in a magnetic field, okay. M star is twice of M, and E star is of course twice of E. Okay, so this is nothing else but EA. Okay, and we have just taken the H cross term outside, I H cross term outside, so this leaves behind this factor. Okay, this term is just obtained by taking in the above case, if I take IH cross outside, it will give rise to this factor, and of course that will give rise to H cross square. Okay, and you will get this term of your kinetic energy. This is your kinetic energy. So if I take IH cross outside, you will get this term for your kinetic energy. Okay, and B square is of course the magnetostatic energy term. Magnetostatic energy which is in the system. Now if I integrate the total free energy of the superconductor, the total free energy, this is the free energy density, the total free energy is then going to be integrated over the volume, and the total free energy of the superconductor is the free energy in the normal state plus integral dq bar alpha mod psi square plus beta by 2 mod of psi raised to 4 plus h cross square by 2m star, the kinetic energy term, grad minus I E star by h cross a psi the whole square plus b square. Okay, you integrate it over the entire volume of the superconductor. Okay, so here I am not bothering about the units too much. Okay, so sometimes people will write this as 8 pi and so on. Below the b square term they will write, below this term they will write b square, depending on the units of the system. Okay, so below this term you can write b square, 8 pi and so on, but at the moment I am not considering any specific units to describe the system. So now, having written the total free energy of the superconductor, we would like to minimize it. Okay, now the minimization is, now remember there are two parameters for minimization, two parameters for minimizing the free energy of the superconducting state, the total free energy of the superconducting state. One is with respect to the order parameter psi, and the second is with respect to the vector potential A. Okay, so we actually do the minimization by taking psi to psi plus delta psi, and we try to get, so if you do a variation of psi to psi plus delta psi, you try to find out the condition for delta f equal to 0. Okay, and this is the minimization condition. So when you try to do this in the above expression, when you try to do this psi to delta psi and try to put delta f equal to 0, you will get your first Ginzburg-Landau equation, first GL equation, which is alpha psi plus beta psi square psi plus 1 by 4m. Now m star is no longer, we have m star, we have used m star is equal to 2m. Okay, and this is IH cross gradient minus 2EA the whole square psi equal to 0. Okay, and working with gradient is working with this gauge. Okay, divergence of A is equal to 0, working with this gauge, that divergence of E is equal to 0. Okay, you can show that now if you open out the brackets, okay, this is basically the same as 1 by 4m h cross square del square psi minus 4 ie h cross a del psi minus 4 e square a square psi minus alpha psi minus beta mod psi square psi equal to 0. Okay, you can show this expression. You will explicitly get something which looks somewhat like a Schrodinger's equation. This looks like the Schrodinger's equation, where you have h square by 2m, this type of a term, and then this is actually the type of a potential which is coming out, arising out of your this thing, and you have a potential term, and then the energy eigenvalues which are associated with it. So you can write down something which looks like a Schrodinger's equation for the system. Okay, this is the first Ginzburg-Landau equation. This is your first GL equation, and the second GL equation is obtained if you minimize with respect to the vector potential A, that is A going to A plus delta A. If you try to minimize and then delta F is equal to 0, the variation has to be 0 at the minima. Okay, if you do that minimization, then of course you will get something like curl of A plus I h cross by 2 into 2 mass of electron twice of E. Okay, psi star gradient psi minus psi gradient of psi star plus 4 e square by 2m a mod psi square is equal to 0. This is your second Ginzburg-Landau equation. Now you know that curl of A is equal to B and curl of B is equal to mu naught times the current density. Okay, so this above equation, your above Ginzburg-Landau equation, becomes mu naught J is equal to minus I h cross E by twice m, mass of an individual electron, psi star gradient of psi minus psi gradient of psi star minus 2 e square by m a mod psi square. If you recall, this was your Gordon's equation, which you had encountered much earlier when we were trying to show that there are Cooper pairs which are formed inside the system, that the left and right moving momentas actually become equal to 0. Okay, there we had written down such an expression and we had shown that this is your diamagnetic shielding current which is giving rise to your London's equation. Okay, so now through minimization of the Ginzburg-Landau, you come down with exactly the same expression for the current density. Okay, so this is your second Ginzburg-Landau equation. Okay, so I have not actually gone into showing you explicitly the details of the minimization, but if anyone is interested to see minimization details, one can follow Mathematical Physics Afghan chapter 14, or you can look at a paper A.V. Dmitriev Superconducting Science and Technology. This is the name of the journal. Short form is UST. Okay, this is the short form of the journal, Superconducting Science and Technology. Okay, and the volume is 17. Page number is 443 to 447, 2004. Okay, so let me write it a bit clearly. This is the journal where you can find your this is this is year 2004. Okay, so if you want to see the minimization details, namely psi going to psi plus delta psi, and that the free energy variation should be 0, this leads to the first GL equation, okay, from the integral form that I had shown you, and the second minimization, A going to A plus delta A, and your delta F becomes equal to 0. I mean, you have to do this at the minima, you have to put the condition that the variation in free energy is equal to 0. This gives rise to the second GL equation. These two you can find the basic procedure in Afghan chapter 14. Okay, this is the basic procedure is outlined in chapter 14, or A.V. Dimitrov, Superconducting Science and Technology, volume 17, 443, year 2004. Okay, and the important thing is that we land up with two equations. Okay, the first Ginzburg-Landau equation is like a Schrodinger's equation, h cross square by 4m del square psi, and there are additional terms which are coming from the vector potential associated with the magnetic field, and there are these nonlinear terms. This alpha psi looks like an energy eigenvalue, but then there are higher order corrections which are present. Okay, so this is your first Ginzburg-Landau equation, which you get by minimizing psi going to psi plus delta psi, and at the minima your variation in free energy has to be 0. That gives you this first GL equation, and the second GL equation comes about when you do this, namely A going to A plus delta A, and you try to get the minima of the free energy by doing the variation equal to 0, you land up with the second GL equation, which is nothing else but an equation for current density in magnetic field. Okay, quantum mechanically you have seen this sort of an expression, mu naught J. You must have seen this expression earlier, but then in a vector potential you can also show that there is this additional contribution, and this we have seen before earlier. So mu naught J is this term into psi star gradient psi minus psi gradient psi star, and this. So with these two equations we are actually now set to work with superconductors and apply these expressions to calculate the current densities in superconductors placed in a magnetic field, what is the behavior of a superconductor in the absence of a magnetic field, and so on. Okay, what are the states which are possible, and so on. We will try and look at those expressions using these Ginzburg-Landau equations for the superconducting state.